Warm welcome, everybody. Thank you for being here. Get yourselves ready. Grab a notebook, a pencil, or a pen. If you're so bold, we're going to be graphing in this one, so if you get a pen, be careful. But whatever you choose to write with, it's fine. This is math from the void, math coming at you pretty much out of nowhere. And today we have a problem from the 1997 AP Calculus AB exam. This is back in the day before the millennia. And it involves a pretty simple function, one you should be very familiar with from like Algebra 1, honestly. And we're given a graph axes. You can tell that it's not going to be too involved. We don't have anything going on over here. And we also don't have any of these y values listed, so we can presume it's not going to get too crazy. Oh, of course, let me show you all the parts of the problem. Now, I'd like you to give yourself about 12, maybe 15 minutes if you need it. This one is a little bit lengthier than your average AP problem, I think, because of 4 parts here. One of them involving graphing. So you'll notice that part A is either going to go really quickly if you're good at graphing, or it's going to go slowly like molasses. Yeah. So you don't want to be slow like molasses because the AP exam is timed. Even though you get about an hour to do 4 questions that are free response, and so that's 15 minutes per question on average. Some of them might be shorter, some of them might be longer. I think it's safe to prepare for any problem to take you 12 minutes or less. That's the goal. Okay, so there are the other parts of the problem. Feel free to pause the video and see what you can do. And then when you're ready, you can unpause the video, come back, join us, and see how we did it here. All right, let's get started, people. On the axis provided below, sketch the graph of f and shade the region R that is enclosed. So sketch the graph and shade the region that is enclosed by the graph of f and the x-axis and the vertical line x equals 6. So let's draw the function. Of course, it's going to start at x equals 3. And it's going to go sort of like that, right? And then we have the x-axis as a boundary, and then we have this x equals 6 vertical line as a boundary. So we'll just call this here R. There we go. And if we really need a value there, feel free to plug in 6, and this is going to be square root of 3. Okay. All right, so that's part A, done. Hopefully that only took you like 15 seconds maximum. It shouldn't take you more than 15 seconds to do that. I'm doing this very slowly as a demonstration. All right, part B. Find the area of the region described in part A. So they could have kind of combined that into one, but they didn't. So let's find the area of the region. I think the most logical way to do this is to just use dx integration. So we basically have some like very thin strips, and we're adding up these strips from 3 to 6, and the function is x minus 3 in root dx. Now you could do some, shall I say, trickery, because this is equivalent to the integral from 0 to 3 of square root of x dx. I just want to point that out. And so this is basically going to give us 2/3 x to the 3/2. You should be very comfortable with integrating already, and this is going to go from 0 to 3. So if we plug in 0, of course, nothing crazy is going to happen, nothing special. But if we plug in 3, we get 3 to the 3/2, and I see a lot of you students kind of getting stuck with how to do that. So remember that 3 to the 1/2 is just the square root of 3. 3 to the 2/2 is just square root of 3 squared, or 3. And square root 3 to the 3/2, is going to be square root of 3 cubed, which is just 3 and then times another square root of 3. Okay, so I see so many students struggling when they see a 3/2 power or even a 5/2 power. It just means the 1 power and then an extra 1/2, so like a square root right next to it. All right, that is the area of the region. Pretty easy so far. Now let's get complicated. Rather than using the line x equals 6, consider the line x equals w, where w can be any number greater than 3. So we're no longer going to have, this line here. We're just going to have bigger than 3. So it could be a really small region, or it can be a really large region, as long as it's to the right side of x equals 3. Okay, so just imagine that. Let A be the area of the region enclosed by the graph. So instead of using R now, we're going to call that area A, and let's just sort of drag this to like some arbitrary place out here, just to indicate that it could be at some different place. And this is going to be A of x. Right, an integral expression. Oh, sorry, it's going to be A of w. That's what we're calling it. Where w is the exact value here, where we drew the line. It's the area enclosed by that region. Write an integral expression for A of w. So it's basically still just the integral from 3 to w of square root of x minus 3 dx. It's really not that bad. And they just want the integral expression. They don't need us to actually evaluate this. It says write an integral expression. It does not say to evaluate the integral in terms of w. Otherwise, we would have to do some power rule stuff, use substitution, and we would get some other answer there. And of course, we could do the same tactic that we did last time. We can just sort of subtract 3 from those limits. We can go from 0 to w minus 3 of the square root of x dx. So that's another way to write it if you like. I don't think you have to do that final one, but it is kind of nice to use the same thing we did in part B. Makes sense to do it like that. Now, part D, let A of w be as described. So I'm going to choose to call it this one here, the second one. You can choose whichever one you want. Find the rate of change of A with respect to w when w equals 6. So we want derivative with respect to w of the integral from, let's say, 0 to w minus 3 of the square root of x dx. This looks a whole lot like when we use the Fundamental Theorem of Calculus part 2, you might know it as, and it looks something like this. d dx from 0 to, it would be x minus 3 square root of t dt. That's kind of how we would see it. So I want you to remember that for the Fundamental Theorem of Calculus part 2, where we're taking a derivative of an integral, I want you to just write f of b minus f of a. And by f, you can, moving my bubble. You can say that f is the antiderivative, or is an antiderivative of square root t. Just say it like that. You could actually take the antiderivative, but it's too long, so we don't have to do that. We want to take a derivative now, so this is going to go back to square root of, well, now it's w minus 3, I guess. Let's get that right, because we are really taking the derivative of this. So this is going to be the derivative with respect to w of f of w minus 3 minus f of 0. So the same kind of thing applies here, where we're just going to end up with square root of w minus 3. And then the derivative of a constant just goes to 0. So that is the derivative of a with respect to w, but we need to plug in this initial condition, w equals 6. Wowza. Which is just the square root of 3. And that kind of makes sense, because if we look at the original function, that is where it meets it when x equals 6, that is. So if we picked the line to be at 6, then the value at 6 would just be the square root of 3. We kind of saw that earlier when we plugged in 6. Okay, so root 3 would be the derivative of the area. In other words, how fast is the area changing? Well, that depends on the value of the actual function. So this is equivalent to just f of 6. Okay, so we had to use our integration methods for part B, and then we had to sort of theoretically set up an integral for part C. This was a very easy to work with function. So if you're not familiar with the square root function by now, honestly, there's the door. Like seriously. So you need to be able to sketch a graph like this, okay? If you can't sketch the graph, you don't really have much hope for the problem because you wouldn't know how to set up the integral. You wouldn't really know how to move this line. Yeah, you gotta understand the square root function. Okay, I think that's enough blab out of me. I'll see you guys next time in the void.